Thank you very much for the introduction and for the invitation to speak today. I was especially interested to know that this is being introduced as an artistic session. It's wonderful. When I proposed this talk, it was a few months back now, and I guess what I want to talk about has shifted a little bit. I do want to talk about geometry, I do want to talk about algorithms, and I do want to talk about data, but mostly I want to talk about robustness. So I'll get into what that means. But first, just to offer a little bit more background, as Charlie said, I have a PhD in mathematics, a background in fine art as well. I find myself working for Mesh Consultants. We're a Toronto-based consultancy, and we really tackle all things geometric. So we solve critical geometry problems in industry, and industry ranges from architecture to engineering. I had a meeting yesterday with a knitting machine company talking about 3D knitting. We work with artists, entrepreneurs sometimes. So we cover a really broad range, but the common theme is geometry. And so today I want to talk about robustness. And the claim that I put before you is that the AEC industry suffers from a lack of robustness. So what do I mean when I say robustness? Here I feel like this word has been, I feel like it's kind of come onto my radar a lot in the past few years. So we can define robustness as the ability of a system to cope with errors during execution or erroneous input. So this definition is actually straight out of computer science, but I think this is a pretty broadly applicable definition. And of course, lack of robustness hurts the budget of architecture projects. But we also have this additional challenge, which is climate change. And this is asking a lot of the AEC industry as well. We know that the building industry is a huge contributor to global emissions, and the industry is forced to change as a result. So in order to kind of address that need, I would argue that we need data about the way our buildings perform. We also need data to advance machine learning in architecture, and I've been really inspired by the conversations this morning and yesterday about data. I'm going to be talking about that a lot today as well. We also need analysis to detect modes of failure. So this is a big part of robustness, is figuring out where errors happen. What we want is risk-aware, performant projects that reduce waste, both material waste and budgetary waste. And we also, of course, want to realize our design intent. So what I want to propose today in this talk is that the idea of robustness can guide us toward better performance, stronger models, better modeling, and more successful projects. And I mean this both literally in terms of making our projects stronger, but I also mean it as a metaphor. So let me try to explain what I mean. So I'm going to be talking about robustness on kind of 3 different scales. The first scale is robustness at the level of operation, and this is really maybe this is the heavy-duty math part of the talk, so sorry that it's after lunch. But so geometric robustness is a problem of very, very small details that have very large implications. So I know you are all computational people. You're probably aware of the fact that not every real number is representable as a binary number. So in other words, there's this discrepancy between machine representable numbers and real numbers. Or put another way, there's a difference between what we imagine numbers to be and what we can make a computer do. And so I wonder how many of you have written a line of code like this: if A is equal to B, then do a thing. Right? We've probably all done this, and it's not bad. But the question is, how do you actually do that first part of the phrase? How do you do A equals B? How do you test this? So actually, this is hard enough with numbers, but once we start talking about geometry, it gets even more thorny. So this is what's known as the coincidence predicate. So in in geometry, at the level of computation, we're talking about predicates. So these are kind of like the very, very basic geometric computations that get to happen behind the scenes of all the other geometry that's happening. So the coincidence predicate is when are P and Q the same point? And how do we test this? So in fact, here we have two pretty reasonable ways of computing this coincidence. This one here, the spherical one, so you might ask, when is the point Q within a small ball of radius epsilon of the point P? That makes a lot of sense, but on the other hand, so does this other definition. So in this case, we're taking differences along each of the coordinates, x, y, and z. This also makes sense, and you can actually imagine a scenario in which you're using one library that's computing the coincidence predicate in one way, and you've written some code that computes it in another way, or maybe you're taking cross-sections or something, and it makes sense to define it in the difference scheme. But I can actually fit the sphere inside the rectangle, right? So in fact, you'll find that there are going to be points that might be outside of that sphere of coincidence, but inside the rectangle. So as you can see, different tests will give you different results for these coincidence measures. So here's another geometric predicate. So in this case, we're asking the question, is that point C to the left of the line through A and B, or to the right? Or does it lie on the line? And I think this is so interesting because it's so easy for us as humans to detect this. But when we actually try to get a computer to do this, it becomes a lot more challenging. And so, in fact, the way this is computed is just a 3-by-3 determinant. This is not a scary thing. This is multiplication and addition. These operations are actually robust. You get into trouble once you start computing square roots or dividing. This is where you get into the territory of irrational numbers. These are very, very much more challenging. But even with this fairly straightforward calculation, a lot can go wrong. So I thought this example was really amazing. The authors of this paper, I can give you their names at the end, but they did this little experiment where they looked at floating point neighborhoods of a point and computed the orientation predicate. And so they take a line, and that point P, each pixel represents a floating point neighborhood. And so the yellow there is what our orientation predicate determines to be on that line. And you can see the shape of this. I mean, does that yellow thing really look like a line? No, right? So I think it's kind of amazing to think that these quantities that we think of as being very precise, in fact, this is what's actually going on. And of course, here's the metaphor that without some kind of firm foundation, without these geometric predicates being robust, how can we possibly expect reliable results out of our algorithms or projects or methods? Now, all hope is not lost. There are certainly things we can do to make these things more robust. Many of you are probably familiar with exact computing paradigms, things like CGAL. I'm not here to argue that as architects you should be using exact computing paradigms. Most of the time the software that you're using does these things very well, and it's fine. If you find that you have a need, please know that there are these packages available to up the precision from floating point precision and up to basically arbitrary precision to compute these geometric predicates correctly all the time. Of course, that comes at a cost, which is usually the time of calculation. It's also interesting to note that architecture in particular is kind of fraught with these things because architects love straight lines. And so you have these coincidence predicates coming up all the time in architecture. Okay, so the second kind of look at robustness that I want to consider today is at a slightly larger scale, looking at the robustness of algorithm or method. And so here, my claim is that robustness at this scale can only be achieved through very large amounts of data and collaboration. Okay, so I'm guessing that many of you have probably seen this bunny. This is known as the Stanford bunny. And it's ubiquitous in computer graphics papers. So pretty much any computer graphics paper you read will have this poor old bunny in it, and they do all kinds of things to the bunny, right? But why is it that way? So one reason is that the bunny was some really early geometry when we had none. So this was like one of the first sort of triangle meshes available for people to do stuff with. But the other reason, of course, is that it provides a benchmark. So if you're doing a new geometry processing algorithm, you should run it on the bunny and see what happens, because everyone runs their things on the bunny, and then you have something to compare against. So I was really inspired earlier this year by a talk by James Zhu of Adobe, and he was talking about the idea of exhaustive validation. And so he was particularly talking about this in the context of geometry processing algorithms. So these are algorithms that would take in a triangle mesh and do something. And his sort of definition of an algorithm being correct is it's correct if it does not fail, which seems fairly straightforward, but what does it actually mean to not fail? We need very big data sets to test whether or not an algorithm fails. And so I think this goes back to the floating point precision question. We can maybe prove that an algorithm is correct. It's a different thing when we move to computation. There we need to exhaustively test it before we can really be confident that it's going to work on any input and cope with these erroneous inputs. Recently, there's been a big push to generalize some of the ideas and the successes of machine learning to 3D geometry. I think this is a really interesting idea for architecture because you are obviously working in the land of 3D geometry. And there's been some attempts to collect databases of 3D CAD geometry explicitly for machine learning. And so James Zhu might say an algorithm is correct if it does not fail on the ABC dataset, which has 1 million items. So ABC dataset, by the way, is a big CAD dataset. And this is available for you to test your algorithms on if you so desire. But it's interesting to look at the overview of these datasets over time. Like they started out very small, and maybe I could have put the Stanford bunny up there first. They started out very small, and they get bigger and bigger. And they're designed, especially the later ones like Thingy 10K and the ABC datasets, they're designed with the idea of benchmarking and exhaustive validation in mind. So my question for you is, what would make a dataset geometrically relevant? And so actually, before I get there, maybe it's worth saying that Thingy 10K and the ABC dataset are both culled from online repositories of 3D printing geometry, typically. Actually, sorry, the ABC dataset is from Onshape, which tends to be for fabrication. So the point is, these datasets are coming from the world of fabrication and 3D printing, which I would argue has a kind of separate set of concerns from those of architects. Oftentimes, architects tend to use meshes in slightly different ways, where the meshes may have kind of semantic meaning. Faces of a mesh might be panels or doors or windows and so on. So the question is, what is geometrically relevant for architects? Do the current databases satisfy that? And if not, where is the data? And up to now, I mean, currently, to use machine learning in architecture, we really need a lot of data. Of course, it's a very hot topic to try to figure out how we can do learning on little data, the way children do. But for now, the best methods we have work when we have a lot of data. So we don't just need architecturally relevant data, we need a lot of it. We also, if we want to measure performance, we're going to need real data. So there's been already some discussion today about these kind of feedback mechanisms between performance and as-built conditions and feeding that back into the design phase. I think that's really, really important, and I think data can help this, but we need to collect it. And finally, I believe as well that to really address climate change in this industry, we also need data for this, that we need to be accountable and measure performance in order to, to tackle this. And I believe that we are going to need a kind of shared effort on this front. By the way, this image is from a really nice effort by Thornton Tomasetti to look at performance measures from architectural massing using machine learning. And one of the things that the authors note here is that the data is all simulated. And of course, what would be, like, this is a really interesting result. What would be even more interesting is if we use a process like this on real data with some noise. Okay, so the last sort of look at robustness is at a zoomed out level still. So I want to talk about robustness at the level of a project. And here, I'm going to move into kind of a probabilistic mode and talk about designing with uncertainty, where we can think of uncertainty as a lack of robustness. And so here, the claim is that using a probabilistic approach to project management can identify critical areas that may signal lack of robustness, or can kind of pinpoint our efforts in certain critical places. Okay, so this is the only theorem and the only equation of the talk, but it's in emojis. I did have like a slight identity crisis when I made this slide, but I think I'm over it now. So Bayes' theorem is a theorem in probability which tries to use prior information to kind of update probability. So it's a little hard to see on the slide, but the question is, what is the probability that it will rain given that it is cloudy? Okay, so on any given day, the probability of rain is probably something like, I don't know what it would be in New York, maybe like 20% rain. So I guess I could step out the door and say it's 20% chance of rain today. But I could also look out the window and say, actually, I see dark clouds, and I know something about dark clouds, which is that they sometimes signal rain. So Bayes' theorem at heart is just kind of encapsulating that reasoning, that if there are dark clouds, it's more likely to rain. So we're incorporating this prior knowledge about dark clouds into our estimate of whether or not it will rain. Bayesian networks are a generalization of Bayes' theorem to to multiple events and complex systems. So these were developed by Judea Pearl, who's a statistician. He's written this book called The Book of Why, which I highly recommend. It's a general audience, like a popular math book, and I would recommend it. It's very interesting. But so the idea is that we can kind of create this network or this abstract graph that represents a series of connected events. So the nodes in this case represent the states. So here the state is whether it's cloudy or not cloudy, whether it's raining or not raining. And the edges would represent the conditional probabilities. So here each node comes with its own conditional probability table, so that the node of cloudy or not cloudy is just this single, it's maybe 50-50 chance that it's going to be cloudy or not cloudy. But the node that represents the rain takes into consideration whether or not it's cloudy. Okay. And we can kind of build these things up to more complex stories. This is one, maybe I have a dog that barks when it's raining, but the dog also barks when it sees a cat. And so how do you actually update this, update the probability that the dog will bark? Bayesian networks give us a way of encapsulating this information and doing those calculations. So, at Mesh, we were really interested in the idea of whether we can use these Bayesian networks in an architectural setting to model projects. And what we found was that modeling a project in this way allows us to identify areas of very strong influence, areas that, parts of the project pipeline that have a strong influence on other parts of the project. So this is all joint work with Daniel Hambleton, and we wrote a sample, like a prototype application in C++ using the open source machine learning library dlib, and that was to calculate the probabilities. So let's look at a couple of case studies. So one of the projects that we have right now is a roof system. And this is probably a fairly common kind of story. We start with some design surface, we have a timber model, and then we have several roof systems that have to go on that timber model, and then we have a panel installation on those roof systems. At the very end is the work product. This is like the successful roof. So this is known as a causal chain. So the successful output of each node just feeds right into the next node. But what's kind of interesting is that even when the chance of success of all of those blue nodes, even when the chance of success of each of them individually is quite high, the final success of the project is still maybe lower than you would expect at 70%. Okay. So we can always ask ourselves, well, how can we do better here? What happens if there's evidence of failure somewhere along the chain? Okay, this is not terribly surprising, right? In this case, the probability of success drops dramatically. So this is actually a project we have at the office right now, and this roof, the panel installation on a roof, and what we're coping with right now is the fact that the as-built condition diverges actually really dramatically from what was modeled. So we can update the Bayesian network to encapsulate this, and this adds uncertainty to the model. So what ends up happening is that when we look at the probability of success of the final roof, we find that it's very sensitive to this divergence of the modeling effort and the as-built condition. So looking at the Bayesian network can allow us to make some decisions. So maybe the decision that gets made is that we need to design panels that can handle a lot of variation. When we did our modeling, we assumed something about how the roof was going to turn out, but that didn't turn out to be correct. So how can we design the panels with that in mind? Or similarly, can we build some kind of feedback loop between the actual site condition and the as-built condition that feeds back into the model? I don't know how I'm doing for time, but a few more minutes. Okay. So maybe just to look at a couple more case studies that are sort of just slightly more complex. Actually, this one is deceptively simple. Okay, so this was a project. We interviewed the fabricator of this project. It was not a mesh project. This was done by Make Studio, and it was this art sort of installation in Victoria, BC. So the Mani was doing the whole thing. He was designing, fabricating, and installing. So it was the complete process. And what he found was that there was this sort of unlikely actor that came up that required significant changes to the design, and that was the site condition. So when the results of the geotechnical review came in, it turned out that the proposed design was just totally inappropriate, and he was left with changes. He can either change the foundation of the structure, or he can change the height of the structure. So what really happened here was that he had made an assumption about the site condition that turned out to be false. And so in other words, he had assigned a biased probability to that site condition. So we might ask what the Bayesian network tells us about how to design this. And once again, it could be a couple things. It could be, well, it would be nice to have that geotech report earlier. Definitely not always possible. But you could also look at it as a way of imposing a functional requirement on the design model to allow it to be adjustable in height. So we could have built that in advance instead of having that be a cost that gets piled on at the end. Oh yeah, right. So with the site condition being poor, the probability of success dropped right down. And maybe I won't actually say too much about this one other than to say that you can develop these Bayesian networks in a much more, they can get much bigger. In this case, you see that the conceptual mass node has a lot of dependencies, so a lot of things feed into it. And that means that it carries great weight in terms of what it means downstream. So, so looking at the Bayesian network, we might decide, okay, we really need to spend more time on that conceptual mass level. So in this case, the project was a panel system for a theater, maybe not unlike this one, but the panels had all kinds of needs. They had acoustic requirements, lighting requirements, there was a pulley system involved. So it was very, there was sort of a lot of detail that went into the design of those panels, and so a lot of things depended on how good that design was. So in this sense, the claim about Bayesian networks is that we can increase the overall value of a project by trying to predict the lack of robustness in advance. And if we can use these Bayesian networks to kind of identify critical areas, we might end up spending more of the budget modeling those areas than we would otherwise, but the idea is that it's going to mitigate the risk and save costs downstream. So in other words, the kind of functional requirements imposed by the Bayesian network have the potential to really increase the robustness of the project. Okay, so robustness, we saw three ideas from the very small level of geometric operation and geometric predicates. We saw that this has big impacts that carry forward into the level of the algorithm and the level of the project. And this is kind of a little bit of a metaphor. At the level of the algorithm, here the process is data-driven and exhaustive. And I'm claiming that we need a lot more data if we want to really use machine learning meaningfully and also to tackle some of the critical issues coming up as a result of the changing climate. And finally, looking at the level of the project, we can use Bayesian networks as kind of a risk management approach to increase the robustness of our projects. I have plenty of references to share if you're interested in learning more about any of this stuff. Otherwise, thank you very much for your attention.